Good afternoon. My name is Matthias Deeg. In the next couple of minutes, I want to talk about mice and keyboards, especially the security of so-called modern wireless desktop sets. Some words about me. I work as an IT security consultant for a company called SySS since 2007. I'm interested in information technology since I was a little kid. And especially IT security. I studied computer science at the University of Ulm in Germany a long time ago. And I did this research together with my colleague, Mr. Gerhard Klostermeier. He unfortunately couldn't be here today, so I'll present this talk on my own. And Mr. Klostermeier is also very interested in information technology, especially IT security. He studied IT security at the University of Aalen and also works as a colleague of mine as IT security consultant since 2014. The agenda of this talk is as follows. At first, I want to give a short introduction about the use technology of this research. I will shortly present the previous work of other researchers that our research is based on. Then we'll give a short overview of our research that we did. Then I will talk about the attack surface and attack scenarios concerning the tested devices, so wireless keyboards and wireless mice. And then there's the interesting part, the found security vulnerabilities of our research. I will also show some demos. Some are not live, so I have videos, but at the end of the talk, I will also try to show one demo, and I hope the demo gods are with me today. And of course, there will be conclusion recommendations or recommendation and Q&A after the talk. So, what I'm going to talk about is actually this, what we can see here on the picture. On the upper row, you can see a target device. In this case, it's a wireless desktop set from Microsoft. It's a Desktop 2000, actually. And the desktop set consists of a keyboard, a mouse, and a dongle. I know everybody here in this room knows. And in the lower row of the picture, you can see some devices I and my colleague have used for analysis purposes. So on the left, you can see a software-defined radio. I, for example, used a Hacktivity 1 made by Great Scott Gadgets by Mike Osman. It's a great device. Then we've also used a crazy radio PA. I will use this kind of device I have here in my hand afterwards in the live demo. And I have also a Logitech unifying receiver right here in my hand. It's very small. Some of you may also own such a device. And you can actually perform all the tests I will show here using a Logitech unifying receiver that costs 16 euros, I think, on Amazon right now. Okay, on this slide you can see how wireless devices actually work. It's easy as shown here. You have a keyboard that sends keystrokes wirelessly, so over the air using radio communication, to a USB dongle that works as a receiver. And this USB dongle is plugged into your PC, and then you have a human interface device, and you can have user input on your PC. And the same is with the mouse. So you have a wireless mouse. It also communicates using radio data communication with the USB dongle and sends, in this case, specific mouse actions like mouse movements or mouse clicks to the dongle. Concerning the previous work, our research is based on, there are actually 4 projects. It started back in 2009, what our research is based on with Kikeriki. It was actually 2009 with the version 1.0 and 2010 with the version 2 of Kikeriki. It was research done by Dreamlab Technologies, Max Moser and Thorsten Schröder, who had a look at wireless desktop sets and found some vulnerabilities. For example, they were able to break the proprietary encryption of the Microsoft wireless desktop set in the 27 megahertz keyboard, and they also had a look in a 2.4 gigahertz technology that was used by some other keyboards later on, for example, also Microsoft wireless desktop sets and Logitech. Then in 2011, Travis Goodspeed, who was also here, attended this conference, we released an article about the promiscuity of this specific transmitter that is used in these kind of devices, and he was able to improve the work done by the Dreamlab guys and found a very interesting, cool way to sniff this kind of radio communication with only one device, one radio. Last year there was the release of a tool called Keysweeper. It is part of the so-called NSA playset by Semicamcar, and this is actually a better version of Kikeriki. I think it fits in a USB power connector and can sniff the proprietary data communication that was also sniffable by Kikeriki, and you can decrypt the data communication and send it via other radio communication outside of a building, and you can sniff on wireless keyboards. And then in February this year, MouseCheck was released. This is a set of actually different vulnerabilities in devices like wireless mice and wireless keyboard, and this research was done by Mark Newland of Bastille Networks, and we also use some of the tools, as we see later on, that Mark Newland has released in February and later on. So our research actually started way back in April 2015 as a customer project. So one of our customers wanted us to have a look at actual 3 wireless desktop sets that are using AES encryption. So in our research we only looked at devices that had AES encryption. So we actually tested different devices, but during the customer project we were not able to find all the vulnerabilities I will be talking here right now, because the duration was rather limited of this project. And in the end, we had a look at the 5 devices that are listed here. So Microsoft Wireless Desktop 2000, a Cherry AES-B Unlimited, a Fujitsu Wireless Keyboard Set LX 901, a Logitech MK520, and a Perix Periduo 710W. We bought these devices because they were all available in Germany via Amazon and were shipped within 1 day. So that was actually how we found these devices, via search query on Amazon, wireless desktop set AES, and that's what we got. Our research actually was very fragmented due to more important things like doing work for money to pay the rent. So there were times where we didn't do anything on this project for a couple of months. So rather fragmented. Here's just a picture showing the boxes of all the devices that we've tested. So our test methodology, we did several things with the devices. They're a general approach that you will do when you have such a hardware device. So the first thing was hardware analysis. So we were opening up the keyboards, the mice, and the USB dongles. We stared at the circuit boards, tried to identify all the chips, or at least the interesting chips. We were reading the fine documentation that we found concerning these chips. We tried to find some interesting test points on the PCBs, and of course we were soldering some wires and tried to dump flash memory that we actually were able to achieve on some of the devices rather easily, as we will see in a few slides. So when we were able to dump actual firmware, we of course could analyze this using IDA Pro. The target devices mostly used a system on a chip, a Nordic semiconductor transceiver, actually with a 8051 microcontroller. So we were staring at some disassemblies for quite some time, read some more fine documentation, and of course we were checking Nordic Semiconductor's NRF24 software development kit, which was very helpful. We also read some code, we wrote some code, did some analysis to find out how the compiler actually worked for this platform, because we didn't have that much experience with this device and also with 8051. So we had to learn some stuff. And the third thing we did during our test, our research, was radio-based analysis, and this was completely new to me. So this project actually is the first project I did using a software-defined radio. So what I personally did is I watched Mike Osman's great software-defined radio video tutorials that are freely available online, actually several times, to know what I had to do with the HackerF in my case. And I also read some more documentation that we found during our research process. We also found out that actually the NRF24, or the family of the NRF24 radios, meaning transceivers, transmitters, receivers, and also transceivers, are quite popular in the maker scene, and that many devices actually use them. Also, the devices that the guys from Dream Labs analyzed back in 2009 and at least in 2010 used one of the nRF24 radio devices. So we also started playing around with GNU Radio, wrote some Python scripts, analyzed the nRF24 data communication using freely available tools like the nRF24 BTLE decoder that we could find. And yeah, after Bastille released their mousecheck vulnerabilities and their toolset in February of this year, we changed our toolset because their toolset was superior to ours. So yeah, it was easier to do some stuff than it was to do in GNU Radio, actually. So on this slide, you can see the identified transceivers and system-on chips we found in our 5 test devices. And as you can see, 4 of the 5 test devices actually used the same low-power 2.4 gigahertz nRF transceiver made by Nordic Semiconductor. So we decided to focus on this transceiver, actually. Yeah, and as I already mentioned, we read a lot of documentation, a lot of data sheets, and it's very important. And it's very important to read them several times because you may miss some important facts there actually standing there, information the manufacturer gives you. In my opinion, the Nordic Semiconductor's data sheets for the nRF24 are very good. Everything is in there that you need to know about the device. And as already mentioned, these devices are very popular in the maker scene, and many people are using them for different stuff, home optimization things, sensor networks, because they're low power, they are cheap. Yeah. And we also use freely available software tools. I already mentioned the nRF24 BTLE decoder, and we also used nRFproc, which was freely available and still is freely available to read and write flash memory of these devices. So in the next couple of slides, I have some excerpts from the data sheets. Here you can see the actual Nordic Semiconductor transceiver we dealt with in the 4 devices under test, and everything is good documented or well documented. The most important pins for us actually were SPI, so serial interface, where we hoped to get access to the memory. And on the lower side of the slide, you can see these transceivers by Nordic Semiconductor actually support readback protection, but as you can guess, not all devices use this readback protection, so we could just simply access sensitive data, like firmware. One other important thing concerning specific versions of the Nordic Semiconductor transceiver we dealt with is that the data memory is divided into 2 parts. One part is addressable via SPI externally, and the other part is only addressable internally via the microcontroller. So in order to get to some interesting data, meaning encryption keys, we had to write our own firmware to actually get access to all the data that was on there. But this was also rather easy. On this data sheet, you can see the enhanced shock burst protocol. It's a proprietary radio communication protocol by Nordic Semiconductor that is used in these transceivers. The details are not that important now. In the first step, it was because we used GNU Radio and had to know, well, what was actually going on, what's the preamble, address, packet control, checksum, and so on. Later on, we just focused on the payload, and the payload actually was AES encrypted. So we just wanted to know how can we attack these kind of devices, maybe. And in the lower table, you can see that the Nordic Semiconductor transceiver actually supports hardware AES encryption in some way, and it's also used in the firmware. So here's an example of a PCB, the backside actually of a Microsoft wireless keyboard, and Microsoft was so nice to label all the interesting contacts or test points for us. So as you can see, the interesting SPI contacts, MISO, MOSI, chip select, clock, you just knew where they were. And the program pin was also labeled, and the reset pin. So this was rather easy to get access to this device. And concerning the Cherry keyboard, we had to do some tests, but within a couple of minutes we also had the test points, and this is a test setup using a bus pirate just to communicate with the transceiver and get read and write access to the data flash memory Yeah, and we did the same thing not only with the keyboards but also with the dongles, because we just wanted to know where's the AES key stored, for example. So yeah, thanks to my colleague Alexander Strassheim, who did the soldering work right here, made a little breakout board, yeah, and we could also gain access on this device. Then, as mentioned before, we did some firmware analysis using IDA Pro, and here it was very helpful actually to have the SDK, so we could identify commonly used libraries with this platform and just annotate the interesting functions for us, the security-related functions, for example, concerning AES encryption, as you can see here. Yeah, and regarding radio-based analysis, we initially used GNU Radio and the NRF24 BTLE decoder that was readily available, and a sample output is shown here. I think it's from a Cherry device, and yeah, so that was our first step concerning radio-based analysis, so we were able just to receive all the data packets sent over the air, and yeah, this was rather helpful. And as mentioned before, after Bastille released their tool set this February with their mouse check vulnerabilities, we also switched to their superior NRF24 tool set, meaning that we didn't use GNU Radio anymore for analysis purposes and also for attack purposes, because it was more reliable to switch to another platform, and this platform was actually the Crazy Radio PA. It's a remote control for a quadrocopter from a Swedish company, Bitcraze. There's an open source firmware for this quadrocopter remote control, and Bastille enhanced this firmware, naming it the NRF Research firmware. And they also released some Python tools, namely NRF24 Sniffer and NRF Scanner, and some other tools that you can just simply use in this combination. And this Crazy Radio is also not that expensive, I think 30 euros including the antenna to play around with. So we developed all our Python tools using Crazy Radio PA and the NRF Research firmware, because it's very, very easy. Yeah, and of course we encountered some problems and had some solutions, but not for all problems. So what I personally learned is that software-defined radio actually has a rather steep learning curve if you've never done this kind of stuff before. So some things that I thought might be easy are not that easy, actually. For example, replay attacks. Yeah. Because there are some things you have to be aware of, for example, channel hopping concerning radio-based devices. There are timing issues if there are specific protocols implemented, and yeah, it's simply not that easy. And also correctly identifying chips when you have a look at the labels when doing analysis of the PCBs is not in itself, because, for example, we just missed that there's also a one-time programmable version of the transceiver that's, for example, used in the Microsoft device. Yeah, and we, for example, bricked one of the Microsoft keyboards in this way, playing around with it without being aware that it's one-time programmable, actually. Yeah, and what is true in general is that using a development kit or a board with the same technology as the target device you are testing is really helpful and saves a lot of time. And the availability of proper tool sets actually makes a real difference, and this is true for all technologies. Yeah, so what's the attack surface and the attack scenarios concerning the devices I'm talking about? Yeah, in our opinion, there are actually two scenarios or two approaches. One where the attacker has physical access to the wireless desktop set, and one where you can just attack these kind of devices via radio signals, meaning over the air and remotely with some physical proximity, but you don't have to have direct access to a device. With physical access, you can do different things that can be considered a security issue, for example, extracting the firmware, manipulating the firmware, extracting cryptographic keys, or manipulating cryptographic keys. Concerning attacking via radio signals, you can do other stuff. For example, simply exploiting unencrypted and or unauthenticated radio communication. You can try to do simple replay attacks. You can maybe do keystroke injection attacks, or you can maybe decrypt encrypted data communication. So here are the security vulnerabilities we found in the 5 devices under test. The first one was insufficient protection of code, in this case meaning the firmware, and data, meaning cryptographic keys. The second one was unencrypted and unauthenticated data communication of these wireless desktop sets using AES encryption. Then we found missing protection against replay attacks, and we also found insufficient protection against replay attacks. And the last one was cryptographic issues that we were also able to exploit. So here, the first security vulnerability, insufficient protection of code and data. What this means is, this is just a slide with an example code. It's a memory copy firmware we have just written to access the flash data memory that's not externally addressable via SPI. So this is all it needs to just copy from the extended endurance RAM, what it's called, to the not extended endurance RAM. Then you can just dump this data using SPI by having access to the correct interface via the test points. So we were actually able to dump the firmware of 3 of the 4 devices that used NRF24 communication. We were able to get access to the firmware and the cryptographic key. So here's an example of a Cherry keyboard and a Cherry dongle, and as you can see, we found the same 16 bytes in the dongle and in the keyboard, and it was the AES key that was actually manufactured in the device during the manufacturing process. So embedded flash memory could be easily accessed using SPI with physical access to the devices, and the flash memory often is not protected by the readback protection that is actually implemented in the devices. The only manufacturer that did this was Logitech. Microsoft, Cherry, and Perix did not. And we also found out that it's possible to modify the content of one-time programmable flash memory, so you can change a 1-bit to a 0-bit, but not vice versa. So, for example, concerning the Microsoft wireless keyboard, we can also manipulate the AES key, for example, or we can manipulate the firmware in some limited ways. And what's important to know is that some wireless desktop sets are just permanently paired during the manufacturing process, so there is no way for the end user to change the cryptographic keys in these devices, so you have to trust the manufacturers. The cryptographic key generation is unknown, so I have politely asked some of the manufacturers how they actually do it. Is there a key derivation in some way, or are they randomly generated? But actually nobody replied to these answers. And the conclusion is that an attacker with physical access can either extract the cryptographic key, or he can modify the firmware and or the cryptographic key in some ways he wants to do. And this always reminds me of this picture that was released, I think, 3 years ago, concerning the tailored access operation of the NSA. And what they seem to do is manipulating hardware in post offices. So when it's rather easy to manipulate the device, when you have labeled SPI access points, and you can manipulate a device within 5 or 10 minutes, maybe somebody actually does it in real attacks. Okay, so the next attack I will talk about is mouse spoofing attacks. This one is rather obvious, and it is actually known for a long time. And here I have a short demo video that I want to show you. So let's see video. So this is our so-called NRF24 playset. It consists of several tools, and Radioactive Mouse is actually just one of these tools. And what Radioactive Mouse does is it can conduct so-called mouse spoofing attacks. And here you can see just a mouse spoofing attack against a Windows 7 operating system that is actually operated with a vulnerable wireless desktop set, in this case a Microsoft wireless desktop set. So here the attack is just sped up because it takes some time, I think 3 minutes. We also did a YouTube video a couple of weeks ago and put it online showing the attack in real time. It can be still sped up, but for proof of concept we thought, hey, that's just enough. And I just wanted to have such a video as a reference because when I talk to people, they just say, oh yeah, it's obvious, the mouse communication is unencrypted and unauthenticated, you can do mouse spoofing attacks, but what's the deal? And I say, well, in some cases you could actually have remote code execution with physical proximity. And that's what, this attack actually shows. So now it's slowed down again to the real time. It does a virtual mouse click here. And then we have a simple download and execute PowerShell attack vector executed on this target system. And for example, ransomware like a crypto locker is installed on this device. And this is just an example for remote code execution. So this is just for reference. And yeah, this was the first demo here. So this was mouse spoofing attacks. These are just backup slides that we've seen. And yeah, what's about mouse spoofing attacks? So the radio communication of all tested wireless mice was unencrypted and unauthenticated. By knowing the right mouse data protocol, an attacker can spoof mouse actions, as we've seen, mouse movements and mouse clicks. And by this, he can get control, unauthorized control over the mouse pointer or mouse cursor, actually remotely, because it's radio communication. This is rather old news, but I think it's nevertheless exciting. And it's still exploitable in current modern wireless desktop sets. But this kind of attack is not that reliable, so it doesn't work in 10 of 10 cases actually, so it's based on some heuristics. So there's trial and error involved and good educated guesses, and that is what I did and what I've exploited in the proof of concept attack. So the heuristics actually concern the operating system, so you have to know something about the screen layout and the screen content. The language settings are important concerning the virtual on-screen keyboard that we've seen that is exploited. You also have to know something about the mouse settings that are actually used concerning mouse acceleration on the target device. And yeah, you have to make a good guess about the window position of the virtual on-screen keyboard that I, for example, exploited right here in this remote code execution scenario. But I think it's a good way to go with the defaults. So the defaults of Windows 7 I've put up here of the target device. So I think it's a good educated guess that most of the people don't change the default mouse settings in their Windows operating system. So you have enhanced pointer precision, the mouse acceleration activated actually. You have the default mouse acceleration curve. And you also have a default position of your on-screen keyboard. So it has a fixed position on the screen and it has fixed dimensions if you've never opened it before and moved it around, for example. So I think this is a good guess and works in most of the cases. And we're not using this kind of attack in a targeted attack way, but when you're just targeting a company, you don't have to get code execution on one specific device, but you can have, for example, 100 devices, 500 devices, and if you have code execution remotely on one of these devices, this may be your way to the internal network, for example. Yeah, what I wasn't able to achieve was pixel-perfect control over the mouse pointer. At first I thought, hey, it's deterministic and I just have to find out the algorithm and so on, but it's not that easy actually. It can be done, but more work is just required. And concerning Windows, at least Windows 7, this mouse acceleration magic still is in a driver Win32 cases, and you have to reverse engineer it. There is some fixed point math in it. It's legacy code. I think it's almost 20 years old, the code in there. It has changed a little bit between Windows XP, where you can still find some documentation, and Windows 7, and from Windows 8 to 8.1, and also Windows 10. So the mouse acceleration is a little bit different on these devices, but yeah, that's part of the heuristics that you have to exploit. So the current state is that I've used a handcrafted and slow down mouse action for this attack to make it more reliable, and yeah, it actually works as proof of concept right now. But if somebody puts more work into this, it can be more reliable. Yeah, and the tools that I've used, as mentioned before, is this Python tool, Radioactive Mouse, and the Crazy OPA dongle using Bastille's NRF research firmware. So it's all freely available. Yeah, so the next kind of vulnerability and attack that is resulting, replay attacks. I've also prepared a short demo here, a video demo, but I will also demonstrate it later on doing actual hardware, if the demo gods allow. So let's have a look at the next one. Okay, so I'll just pause for a second right here to describe the setup. No, I wanted to pause. Okay, here's a fade in. So that's just a simple setup. On the left we have the attacker laptop that's connected to a software-defined radio that you can see in the middle on the table. It's the Hacker F1. And on the right you have the target device. It's running Windows 7 in this case, and it's operated with a vulnerable mouse and a wireless keyboard, in this case a Fujitsu wireless desktop set. And what the attacker simply does, he runs GNU Radio with a very simple flow graph, and he just records the wireless data communication, and later on he replays it. So that's a replay attack as simple as it can get. So let's see what this actually can mean. So here's the attacker. He starts GNU Radio, recording the radio communication. Now the victim is, for example, unlocking its Windows operating system. Then the attacker just stops the recording. Sometime later the victim will lock its screen, grab a coffee, and during this time the attacker can just get near the device, replay the recorded data communication. Yeah, and if all goes well, just gets unauthorized access to a foreign system. Yeah. So that's the danger of replay attacks. And I was really surprised that this kind of attack actually worked with one of the devices. And the funny thing is it works with all of the tested devices. So all tested devices are vulnerable to replay attacks. And that's one thing you don't want to have using crypto devices in this way, that a simple replay of the communication has the same effect as it was done before, because there's no session initialization going on using proper crypto and stuff like that. Yeah, so this is just a description of the setup you've seen in the video. And here's the simple flow graph. Concerning GNU Radio, it doesn't get much simpler than that. What I could also disable or leave out is the bandpass filter, but being nice to the neighbors, as Travis always said, is an important thing. But yeah, you actually have a source and a sink. You're recording from the radio to a file, and later on you just switch directions, so we replay from a file to the radio, and that's it. So this attack just takes a couple of minutes, 5 minutes to test the device. And it can also be done as a black box, so you don't have to know anything about the radio communication, you just have to find the right frequency the device is communicating on. That is well documented, and all device actually that is sold in the US has a so-called FCC ID. So you can just research online and have all the information you need. So this is rather easy. And yeah, we've also written a simple Python script that does the same thing using another tool, SET, so not GNU Radio and a software-defined radio, but the Crazy Radio PA and the research firmware and this Python script. And I think here it's an example using a Microsoft wireless keyboard, and you can just record the encrypted data communication and replay it at a later time, and it will just work. It has the same effect as the initial keystrokes. Yeah, so as mentioned before, all keyboards of the tested wireless desktop sets were vulnerable to replay attacks, and all mice too. And the only difference between the devices was that the Microsoft desktop set had actually some kind of replay protection, so the actual attack window is limited. But we don't know actually how small it is. I think it's about 1,000 keystrokes that can happen between the recording and the playback. So it seems to get out of sync, and then it doesn't work. Concerning the other devices, so for example Perix, Logitech or Jerry, we could just replay communication we have recorded the day before or the week before, and it still works. So they're just vulnerable to replay attacks, simple replay attacks. And yeah, replay attacks can, as also already mentioned before, done as so-called black box test. You don't have to know the actual protocol. And more sophisticated attacks can be performed using the other tool set, Crazy Radio PA, Python tools, and the end of research firmware. And replay attacks, as we've seen, allow for the following attacks. You can gain unauthorized access to unattended screen-locked computer systems, where you were able to previously record the password entry. And you're also able to recover the clear text passwords, clear text keystrokes, for example, passwords, when you have physical access to the USB radio dongle of a targeted device. So if you can record the radio communication and later on can get your hands on the USB dongle, you can just steal it or replace it, take it home, stick it in one of your computers, perform a replay attack, and then you will get all the clear text keystrokes that somebody has entered before. So this is also useful, or it can be useful in a keylogger scenario, for example. So the company itself installs all the wireless desktop sets and devices. You're sitting in the office nearby, for example, on another floor. You're just recording communication for several weeks, and then you gain physical access to the devices, replace them, nobody will know, take it home, replay the communication, and you have all the clear text communication of several days or weeks, for example. So a keylogger scenario with one-time physical access, and it's rather stealthy. You need to have one-time physical access to the facility. Okay, and now we are already coming to the last and I think most interesting vulnerability and attack, the so-called keystroke injection attack. And this is the one I want to try live. So now I have to do some preparations. For example, I will here do a live hack concerning picture-in-picture on my display. Let's see if this works out. So I have my target device here. I just have to unlock it. So this is not a real-world example because nobody runs a Windows 7 virtual machine on a MacBook Pro to work, but I couldn't find another device, so sorry for that. So, shoulder surfing using a camera. So, I'll put the camera back. I hope that the autofocus will work on this one. And it's not that important that you can see every character on the device. It's just important that you can see that something actually is happening on the device. So yeah, what I have here is a Cherry wireless desktop set. In this case, this is the receiver, the USB dongle. I'll plug it in here. So it's used by the virtual machine. And here I have a hopefully vulnerable wireless desktop set. I will just test it. Yeah, and you can see there are some keystrokes here in Notepad. So now I'll go to my attacker system and prepare this one. So what I will use here is Crazy Radio PA and the NRF research firmware by Bastille. So many thanks to Mark Newland who actually did this research. And here I have a proof of concept attack tool just to demonstrate two attacks or a combination attack. It's a combination of a replay attack and a keystroke injection attack. So I will fire this up. And so what I will have to do first is scan the devices. So I will just do some key presses, and you can see I can identify the radio communication and find the device. And you can also see there is some output concerning crypto. We will get into this later. Let's first see if the attack actually works. So what I can do now is, for example, recording. So for the replay attack. So as a victim, what I will do is I will lock my screen. As an attacker, I have to press record, and now I'll try to unlock it using the correct password. So this was a success. As an attacker, I stop the recording. Later on, the victim will lock her or his machine again, and then I can just try if I'm able to remotely unlock the device. Let's see if the demo gods help me in this case. As you can see, works perfectly. So this is one way to get unauthorized access with physical proximity to devices that are operated with affected while vulnerable wireless desktop sets. So well, that's not all. The more interesting thing is, oh, now it just went. This is the Mac OS. So, well, it's in the same state. So I hope you can see it. So, and what I can do next as an attacker is, due to other issues, hopefully this. Keystroke injection attack. And as you can see, just a window opened, it's Windows execution. You can see there's a command shell, it's a PowerShell actually. And if we wait some time, we hopefully get remote code execution. Yeah, and it worked. So it's the same mock-up attack vector using ransomware, a crypto locker in this case. I just did a keystroke injection attack using download and execute attack vector as with mouse, the radioactive mouse before. And this means, you have completely control remotely over the affected devices. Okay, so that was the live demo. Let's go back to the slides and see why it works. Yeah, it worked the first time, thanks to the demo gods. Okay, so I can just kill this one here. So yeah, that's another tool we've written. I just showed you another one, so that's a command line interface version, and here we have one with a fancy GUI. It was the Cherry attack tool that we've seen. And now, why does this keystroke injection work? Because this device, this Cherry device, for example, it uses AES encryption, right? It also has AES security written on it. And it's true. And all packets that we've seen so far in the radio communication, they are actually AES encrypted. But there are some issues concerning the mode of operation AES they have used, namely AES encounter mode. So the first thing we thought about is how do they synchronize in any way? And what we found out, and also could read in the SDK, in the libcrypt header file, is that there are differences between two versions of the actual transceiver. There is an LU1 and an LE1, and the implementation is slightly different between these. And the LE implementation, the LS5B, that is here, it's a plain text counter actually, is not a counter, but random values generated by the embedded random number generator. So there is simply no way of syncing between the receiver and the sender, actually. And this is part of the issue in this case. Yeah, and here is actually the source code for generating this random 5-byte or 40-bit value that is used and also transmitted in shock burst packets over the air. And it uses the hardware random number generator. And honestly, I didn't have a look at the hardware random number generator if this has any issues, but maybe it has, maybe it does not. So, but more important, why does the keystroke injection attack work on AES encrypted keyboards? So what we found out concerning the Cherry and the Perix wireless keyboards is that they are using 100-bit keys with AES encounter mode. In general, the initialization vector consists in this case of a nonce and a counter. The nonce of the tested Cherry keyboard and also the Perix keyboard and the Logitech keyboard was null bytes, and the counter, as we've seen in documentation, was just 40 random bits, so 5 bytes. And by manipulating the firmware of the Cherry keyboard, having physical access to the device, having found SPI access points, by being able to dump the firmware, analyzing it using IDA Pro, we could actually find out how Cherry, for example, does all the AES communication and initialization of the data that is transmitted. And what we found out there is that a so-called key release packet consists of 11 null bytes. So when a key is released, a packet is sent, an encrypted packet, but actually the plain text that is sent is this one, 11 null bytes. So when you have a look at how counter mode in general works, for example, for a block cipher like AES, it works like this, shown in a diagram. And when you consider what is known to an attacker in our scenario concerning wireless desktop sets, we know all the things that are marked in red. So we know the complete initialization vector. The nonce, as mentioned before, is always 0. We found this out due to the firmware analysis. The counter is just a 5-byte random value, but it's transmitted over the air, so it's no secret. Everybody can read it. The ciphertext is also transmitted in combination with the counter over the air in the enhanced shock burst payload. The plaintext is something we know for some specific packets, namely every key release packet. So what we can do due to the mode of operation is some kind of known plaintext attack, because the exclusive order that is used in counter mode that you can see here concerning the input values key stream block that comes from the block cipher, that is based on a secret key that we do not have access to because it's in a device and it's never shared, it stays secret. But the XOR operation concerning the input key stream block and plaintext block is this one. We can just, or we just know the key stream block for some specific packets. And that's the important thing, and actually this is the vulnerability why keystroke injection works. So I have an example for this on the other 2 slides and more explanation. So what we know is that the initialization vector actually is only a random value, random 5-byte value, and we already know that it can be reused, with, which is also a security issue because it allows replay attacks as we've seen before. So when we consider a encrypted key release packet consisting of 16 bytes, we have 11 bytes data and we have 5 bytes random value. And that is what you can sniff over the air using a new radio or a device like the Crazy Radio. And now we know that the data of a key release packet is simply 11 null bytes, and we also know that X exclusive or 0 equals X. Simple as that. And what this means is that we have control over a complete data packet with a specific counter value, a specific initialization vector. And this allows for arbitrary manipulation of this kind of packet. And what you also have to know is what is the plaintext data format, but this one was rather easy because all the devices use some kind of the default USB human interface device data format. The Cherry one actually uses this, so we have 8 bytes in total. The first byte is modifiers, for example, a shift key or alt key. Then there's a 0 byte, and then you have just 6 key codes that are sent with one packet. HID packets. An example for modifier keys and key codes, they are also specified in the USB HID specification. And here's an actual example concerning a keystroke with the uppercase letter A. So what we have is we have a key release packet sniffed, and we want to have an uppercase letter A. So the modifier is, for example, shift left plus A. In this case, it means we have a modifier of 01, and the key code, the first key code is just 04. And what we have to do is simple math. We have an exclusive OR with this encrypted packet we sniffed with this one, and have a resulting packet, and that's the one we can simply inject. And the result is, because counters can be actually reused, as in the replay scenario, that the receiver will send a correct keystroke with an uppercase letter A to the PC the dongle is connected to. So keystroke injection in 5 easy steps. You have to find first a target device, but it's easy sniffing it using the toolset we have now available. You have to find a key release packet. This one is also based on heuristics, but the heuristic I use is when the last packet I've seen before a pause of 2 seconds most probably is a key release packet, right? And this works in, well, almost 100%. But radio is not that reliable, but in my test case it was very reliable. And then what you have to do is the simple math, the XOR operation, and then you just send modified key release packets for keystroke injection and repeat until you're done with your attack vector. For example, download, execute, install malware, do whatever you want on the remote system. And here just for illustration, that's all the source code it takes concerning Python for modifying a packet. It's actually here only this XOR operation. Yeah, and my boss also asked me to have a standalone version of this attack, and what we've done is we've picked up an old Raspberry Pi we had lying around, and I've built a Lego box. This was actually the most time-consuming task. The rest was rather easy, and yeah, it's just a Raspberry Pi. As you can see here, so it's a breadboard setup, and with this device, you can simply perform this kind of attack, also the replay attack, the keystroke injection attack. And my boss also told me last week not to put it in the hand luggage when flying, because the airport security may ask some question when they see this kind in the X-ray scanner, hand-soldered PCB. Okay, so and now for the manufacturer statements and feedback, because due to our responsible disclosure program, we are responsible disclosing and coordinating the release of found vulnerabilities with the manufacturers or vendors, and so we've sent security advisories to them. We got no response from Perix, so nothing to say here. Microsoft gave us some feedback concerning the insufficient protection of code and data. They just said, well, if somebody has physical access to the device, he could also just replace it completely, so that's not a real issue, and if you put some more effort in it, he can always dump the firmware in some way. And I think, yeah, that's actually true. It's, I think, the third law of Microsoft's 10 immutable laws of security. But I think you can raise the bar rather easily by simply using the data readback protection that is already there in the device. You just have to activate it in the manufacturing process, and then somebody like me is not able to just connect to the spy test points and dump the firmware within a couple of minutes, and also the key. So yeah, you can raise the bar here. Concerning the unencrypted mouse communication, Microsoft replied, yeah, that this behavior is just by design, and they will not fix it. And concerning replay attacks that we also found in the Microsoft keyboard, they are still some kind of working on it, but I haven't heard from Microsoft since a couple of weeks, so I don't know what's the current status is. Yeah, and Logitech, they just replied, yeah, thank you for notification, and they will provide better encryption in future products, so I hope this will be true. And yeah, Fujitsu, they also said that they will incorporate this knowledge in successor products, actually, but they also said, yeah, we believe the described scenario is not easy to perform, and this concerns only replay attacks in this case. They say it's not that easy to perform under real conditions due to the radio protocol. Yeah, and that you have to be a sophisticated attacker. I think that's not true, because, as I mentioned before, you can actually perform this attack thanks to Mark Newlin from Bastille, using this tiny USB receiver Logitech unifying dongle, flashing a firmware on it, the NRF research firmware, and you can actually perform a replay attack. Yeah. Okay, but it's not my mistake. It's not true for the Fujitsu, okay, because it's another protocol. So for the Fujitsu, you have to have a software-defined radio. Concerning the other devices, you can do it with this one, with the Logitech unifying receiver. But concerning software-defined radios, they become cheaper and cheaper over the last month or years. So you don't have to be a state actor to perform replay attacks. Yeah, and Jerry, they were the first one we contacted, and where we actually found the security vulnerabilities in. Yeah, they just decided not to longer promote the AES encryption, so they are now selling the product not anymore, I think, as AES B Unlimited, so they rebranded device. Yeah, and they recommend their customer to use wired products if they have more security demands in other security-related environments. So, conclusion, all the tested devices, all the 5 of them, had one or more security vulnerabilities. In my opinion, all the found security vulnerabilities can be exploited in real-world attack scenarios. So if I can gain physical access for a couple of minutes, I can extract the firmware. In some cases, I can extract the cryptographic key. I can manipulate the firmware, and I can manipulate cryptographic keys. I can perform replay attacks rather reliably. And concerning devices from Jerry, from Perix, and from Logitech, I can also perform keystroke injection attacks very reliably. Yeah, and as we've seen in the manufacturer feedback or statements, the found security vulnerabilities cannot or will not be fixed in the tested products, but maybe in future ones they won't exist anymore. So on this slide, you can just see a summary of the 5 vulnerabilities. So insufficient protection of code and data means we have access to sensitive data, namely firmware and cryptographic keys. Unencrypted and unauthentic data communication is rather old news, but it's still exploitable if you have the correct heuristics, good educated guesses. Missing protection against replay attacks, allows for replay attacks, and you can use it, as we've seen, to gain unauthorized access with physical proximity to computer systems. And the same is true for insufficient protection concerning the Microsoft case, and cryptographic issues, as we've seen in the AES counter mode encryption, can lead to keystroke injection, where an attacker can remotely execute code on your target machine, just as if he is sitting in front of the machine. So, in this table, it's another summary of our research results. So what we found concerning these 4 actual vulnerability types. As you can see, everywhere where there's a check mark, the attack and the vulnerability exists. Where there is a red X, we were not able to find this vulnerability, and there are still some question marks in there. So concerning the Fujitsu keyword that uses another technology, it's still a work in progress, but I think we can have a look at it beginning of next year, sadly. But we will have a look at it, because it's fun to do. Software-defined radio stuff. And concerning the Microsoft keyword, there's also a question mark concerning keystroke injection, because up to now we still don't know exactly what kind of encryption mode they are using. So it doesn't seem to be the same thing as AES counter mode concerning the Cherry, the Perix, and the Logitech keyword. They do something else, but I'm not sure if it's really secure or not. But I will also have a look at this in the future. Okay, so there's only one recommendation I can give you, actually, and that is not to use wireless desktop sets with known vulnerabilities in security-related environments, because somebody may or can actually exploit them in a real-world attack scenario. And as Radioactive Mouse says, all I want for Christmas is a secure, low-power wireless desktop set. And another thing is, so security awareness, I think, is always a good thing. And I'm a big fan of Mr. Robot, maybe some of you are too. I would like to see some of these attacks, or at least one of the attacks, maybe the combo attack, replaying keystroke injection in the next episode of Mr. Robot when Evil Corp is attacked or something like that. This would be great. And I think it would be a cool security awareness stuff when people can see this kind of attack. Because many devices that are still vulnerable are used, and they won't be replaced for the next few months or years, maybe. Who knows? And here are also some references, reference to the research done by researchers previously, and also to the security advisories we've released concerning this research project. Quite a few. And we also released, as mentioned before, a short YouTube video you can find here. It needs some more views, some more clicks, and here you can see just a complete attack in real time. If you need a reference, if somebody doesn't believe you that it's possible under some circumstances, in some situations, to actually get remote code execution by exploiting an unencrypted, unauthenticated wireless mouse. So thank you very much for your attention, and I will also answer your questions. But I have one more thing that I forgot to mention, because it's not only wireless desktop sets, it's also other devices that use the same technology, and one obvious one is wireless presenters. So this Logitech wireless presenter that some of you use, and also used here, this is my own, they're also vulnerable to keystroke injection attacks. They're not encrypted in any way, but you can spoof them, you can send manipulated data communication, and you have the same effect. You have keystroke injection on unlocked systems in the right time. So, thank you very much.